Okay, so we're going to try to use the method of exact equations to solve this problem. Now, this is in the standard form that we might expect for an exact equation. We have m, some function of x and y, times dx, plus n, some function of x and y, times dy. Now, if we inspect this very carefully, we could actually see that in this particular instance, it may also be possible to solve this as a homogeneous equation. My polynomial here is a second degree polynomial in two variables, as is this one. So it may be possible to solve this equation for dy dx and put everything on one side of the equation and then solve this problem as a homogeneous equation. I don't know how the integration would go. It would probably require integration by parts and some other things that maybe we don't want to do. But we're going to try to solve this one by using the method of exactness. So when we do that, we need to check to see if this is in fact exact. And so we're going to take our m here. M is equal to 3xy minus y squared. And for the thing that we want to test, we're going to find the derivative of m with respect to y. So the dx is here. That means it's already a derivative for x, we think, for some function. And we want to find the derivative for y so we can compare the mixed partial. So the derivative for y is going to be 3x minus 2y. And then we're going to do the same thing for the other function. N is x squared minus xy. And so since this is multiplied by dy, this is already, we hope, a derivative for y. And so what we want to test is the mixed partial of this imaginary function. And so we're going to take the derivative of this for x and get 2x minus y. Now, in a perfect world, if this was in fact exact, then this term and this term would be identical. And then we could just proceed by solving it as an exact equation. They are not identical, but we have a technique to make them identical. So this is not exact as is. Now, in order to make it identical, what we need is an integrating factor that we can multiply the entire original equation by, that after we do that, will make the two partial derivatives exact. Now, there are two versions of the formula that we need to check. And so one of them is the derivative for y that we have already found, minus the derivative for x, which we've already found, divided by n, or a similar function with these two terms flipped, and the denominator switched. Now, if either of these two expressions turn out to be a function of a single variable, then we can proceed to find the integrating factor very similarly to the way that we found the integrating factor in linear equations, using the result of this expression. So if we check the first one, we're going to find that my is 3x minus 2y, and then nx is going to be 2x minus y. And then we're going to divide that by the original n, which is x squared minus xy. And so if we simplify this a little bit, we get 3x minus 2y minus 2x plus y all over x squared minus xy. And the numerator, 3x minus 2x, becomes x. And minus 2y plus y becomes minus y. And the denominator, if we factor out the x, becomes x times x minus y. And so if we cancel out the x minus y's, we get 1 over x. Now, similarly, we could try this with the other function, although we only really need one of them to work. In this case, we would have 2x minus y minus 3x minus 2y, and then we would divide it by 3xy minus y squared. And so 2x minus 3x would be minus x, and minus y minus minus becomes a plus 2y, would become plus y, all over, and if we factor out the y, 3x minus y. And we can see this is not going to cancel. So this is not producing a function of a single variable. This one is producing a function of a single variable. And so what we're going to do is we're going to take this expression that is only in terms of x, and our integrating factor is then going to be mu is going to be equal, just like with the linear equation, e to the integral of our integrating factor expression here, 1 over x dx. And we're integrating with respect to the variable that is here. So this is 1 over x dx, and we get e to the ln x. And the e and the ln can cancel, and we're left with x. So now what we're going to do is we're going to take this integrating factor, and we are going to multiply this through the entire original equation. So let's take our original equation, and we're going to multiply x everywhere. X by that, and x by that, and x by 0 is 0. And so we're going to end up with 3x squared y minus xy squared dx plus x cubed minus x squared y dy equals 0. And so what this should do is it should turn our equation into an exact equation. So now we're going to check. So m is equal to 3x squared y minus xy squared, and then we're going to take the derivative for y. So the derivative for y is going to be 3x squared minus the derivative for y is going to be 2xy. And then we're going to take our n function, x cubed minus x squared y. And we're going to take the derivative of that with respect to x. And that's going to get us 3x squared minus, with respect to x, 2xy. And so now we can see that our two terms are now exact. They are now the same. And so now we can integrate as if it were an exact equation. So we're going to integrate m. So we're going to integrate 3x squared y minus xy squared with respect to x, because that was originally a derivative of x. And if we integrate with respect to x, we get x cubed y. And if we integrate that term with respect to x, we get 1/2 x squared y squared, plus possibly some terms that contain only y. And then in this case, we're going to do the same thing with the other term. We're going to integrate here x cubed minus x squared y dy. With respect to y, well, this is no y's in it, so it's just x cubed y. And then this one, integrating y, we're going to get 1/2 x squared y squared, plus possibly some terms that contain only x. And so then, of course, our phi function, phi of xy, is going to contain the terms that match. So if they have functions of two variables, any terms that contain two variables will appear in both expressions. Let's do green. Okay, so both of these terms contain both variables, both x and y. X cubed y minus 1/2 x squared y squared. If you have terms with two variables that don't match, then you did something wrong. And then if we had any x-only terms, they would appear only here. And if we had only y-only terms, they would appear only here. And if we have none of those, we can't recover the constant in any case. So we would always still have to add our constant of integration. And again, the alternative way of expressing this without the function notation is implicitly 1/2 x squared y squared equals a constant.